Indian private firm Agnikul has launched the country's first kerosene liquid oxygen powered rocket. This is also unique because this rocket is using engines that are 3D printed as opposed to conventionally manufactured engines. We're joined by Srinath Ravichandran, the CEO and co-founder of Agnikul. Srinath, please tell us how momentous is this launch given that this is many firsts?
Yeah, I think it's a very special launch for us because it's proving almost all of our homegrown technologies. As you mentioned, the 3D printed engine, the autopilot algorithm, and it's also from our own private launch pad. So, in a way, that entire setup end to end is getting validated here.
Okay. Tell us why you chose 8 kilometers altitude. Typically, when rockets are test flown, they fly at least up to the upper atmosphere, 60 to 80 kilometers. Why 8 kilometers?
So we had to actually size this rocket around an engine, and we chose the second stage engine of our orbital class vehicle, the Agnibaan full scale vehicle, right? So one thing we wanted to do with that is to test out all the maximum aerodynamic loads that we will face in the orbital flight in this flight itself. So we try to configure a trajectory wherein when we go to a particular altitude, we face the maximum dynamic pressure, the region where the vehicle goes through its maximum loads, and this flight is actually configured to withstand that. So that's why this height.
Simply put, this is actually a trial for bigger things that are to come, right? This is a small rocket, but of course this is made so that you test it out and you can implement the same technologies in your larger rocket.
Yeah, definitely. That's why we are calling it a suborbital tech demonstrator, because we have done everything in terms of software, in terms of electronics, in terms of algorithms, 1:1 as it would be in the orbital vehicle. So making this flight work means orbital flight almost is 100% guaranteed to work.
So what made you choose this unique approach where you have your own launch pad and own mission control? Of course, it's very expensive.
So I think if you look at today ISRO's launches, for example, right, they are also increasing their launch manifest, and going and having the process of integrating with an existing launch pad can be pretty tedious, both in terms of scheduling and also in terms of process. So what we thought we should do is have our own setup in such a way that we are able to be independent from the fluid filling process, the mechanical process, and so on. Of course, you need the launch pad support for the range safety, the flight readiness, and so on. So there is this hybrid approach that we have taken in this one. Gives us flexibility in schedule and also flexibility from our own plumbing and the electrical implementation.
See, this semi-cryogenic or kerosene liquid oxygen combination is very complicated. Kerosene exists at room temperature, liquid oxygen minus 183 degrees centigrade. So how do you pull this off?
I think the interesting part is kerosene actually is easy to handle, and we have actually chosen aviation grade fuel. So aviation grade fuel is the same fuel that planes fly with. So that was one thing that we wanted to solve for. And then liquid oxygen. So liquid nitrogen is actually colder and a lot more people use it. So liquid oxygen only comes with this additional risk of fire hazards. So we tried to work around that aspect, and we were able to build a system where we were able to match these two together. It is one of the most successful fuel combinations in the history of rocketry, and so we knew that if we get this part right, we'll be able to rapidly scale on that part.
But also one very challenging aspect is solid fuel rocketry is older. It's seen as more reliable. Liquids are much more complicated, sophisticated in terms of engineering. Tell us more.
So I think the solid versus liquids debate is a long debate. Rocketry started off from missiles, so they were all solid based, right? And we talk about how Tipu Sultan's era is where the whole rocketry business started and so on. Now what's happening with the current era, if you look at all the other companies that are coming up across the world, everyone is going through this phase of building liquid propellant based stuff because of three reasons, right? One, it is actually super flexible. Second, it allows for a more complicated mission profile to be executed at a lower cost. And third one, I think there are other advantages like reusability, trying to make the whole system more nimble. That's possible with liquids. To get to the point of where we begin, that's a little harder with liquids. But I think one of the things we did with 3D printing actually helped us there. Because if you typically look at a liquid engine, there are like thousands of components and you have to assemble it carefully and you'll have to weld it carefully and so on. For us, in our engine, none of those things exist. So sort of trying to take the good parts of liquid and also make it look like the simplicity of a solid system.
Right. So you talk about manufacturing engines quite rapidly. So what kind of launch frequency are we looking at least theoretically now?
I think to start off with right now, we should be looking at probably one a quarter or so till we get to a point where now we know that we can definitely make orbit every time we launch. And at that point in time, the target is to go to a launch every 2 weeks. And even at our full scale capacity, which is 300 kgs, even if we do 25 launches a year, it's barely scratching the surface in terms of what is the market demand in this segment. So there's a lot more scope for improvement actually.
So how long does it take to build a, or rather 3D print a rocket engine of your size? Of course, it's small, and a large scale engine in conventional manufacturing. How long does it take? Compare, please.
Our engine for our size, it's about 400 mm or so in terms of height. It takes about 72 hours to print, and we actually print 2 of these together in the plate that we have. So that will give us a total of about 2 engines a week, you could say.
Okay. So also tell us the long-term goals, right? So when you have launch vehicles using liquid propellants, one of the ideas is obviously to throttle the engines, restart them, relight them, reuse them. So in that regard, are you working on something?
Yeah, definitely. I think one of the advantages of liquids is this whole reusability and throttleability and so on. So I think when we're actually going for orbital mission, we will have a secondary mission objective to attempt some of the things that will be needed to recover the stage. Now it won't be a full-fledged reusability attempt, right? But at least if there are 10 technologies needed to reuse a spent stage, at least 5-6 should be tried out in that one. So that work is always happening in parallel. Of course, the first goal is to get to orbit. But after that, this is going to be the obvious next one.
Okay, so how long can we expect between your suborbital flight, which you've done, an experiment that you've done today, and the actual orbital flight?
I think it will be at least 9 months. We've learned a lot about what it means to actually build machines that are this complex and launch. So I think conservatively at least 9 months it would take.
Thank you, Srinath. So that was Srinath Ravichandran telling us about their journey in rocketry, and of course the unique approach that they've taken, where conventionally solid fuels is the first approach that most people take, but they've begun with kerosene LOX, which is the first of its kind in India. So that's what is a hope that the company hopes will give them huge dividends in the coming times. From Satish Dhawan Space Center, Sriharikota, Sidharth.M.P, WION World is One.